When discussing Linux distributions, a fascinating observation emerges. Smaller, more streamlined Linux distributions often outperform their larger, more mainstream counterparts. At first glance, this might seem counterintuitive. One might assume that a distribution packed with features, graphical utilities, and pre-installed software should offer a better user experience. However, when you look beneath the surface, the reasons why smaller Linux distributions tend to perform better are both technical and practical, spanning several key aspects of system operation. Performance in computing is largely a function of how efficiently resources such as CPU cycles, RAM, and storage are used, as well as how quickly the operating system can manage input-output operations. Small Linux distributions excel in these areas because they are built with minimalism and efficiency in mind, often leaving out unnecessary software and services that can burden a system. One of the primary reasons small Linux distributions perform better is their lean system architecture. Unlike large distributions that aim to provide a comprehensive user experience out of the box, smaller distributions prioritize essential components. This minimalism means that the operating system has fewer background services, daemons, and system processes consuming CPU cycles and memory. For instance, a standard full-featured Linux distribution might run dozens of services immediately after boot, including update managers, indexing services, desktop search utilities, and multiple logging mechanisms. Each of these consumes system resources and adds overhead. In contrast, a lightweight distribution such as Alpine Linux or TinyCore Linux starts with only the bare minimum necessary to boot the system and provide a functional environment. This results in significantly faster boot times and lower memory usage, which directly translates into better overall system performance. Memory efficiency is another area where small Linux distributions shine. Modern applications and operating systems have become increasingly memory-hungry, often requiring gigabytes of RAM even for basic tasks. By stripping down the operating system and avoiding the inclusion of large libraries, heavyweight desktop environments, and unnecessary graphical effects, small Linux distros minimize their memory footprint. This reduction in RAM usage is particularly beneficial on older hardware or devices with limited memory capacity, where every megabyte counts. For example, lightweight desktop environments such as EAL-XQt, XFCE, or OpenBox are commonly used in small distros because they offer necessary graphical capabilities without the overhead of features like compositing, 3D acceleration, or advanced animations that heavier environments like GNOME or KDE provide. As a result, users experience snappier interactions, faster application launches, and reduced swapping to disk, which can otherwise slow the system considerably. CPU utilization is closely linked to memory efficiency. When the system runs fewer processes in lighter desktop environments, the CPU is less burdened with context switching and background tasks. Large Linux distributions often include automated update processes, background analytics, or integration services that periodically check for system updates, telemetry, or synchronization tasks. While these are convenient, they consume CPU cycles and may interfere with the smooth operation of user applications. Small distributions avoid such overhead by allowing the user to choose which services to run and which to omit. This philosophy gives power users granular control over system resources and ensures that CPU power is directed toward active tasks rather than background management. For users running performance-sensitive applications, such as development environments, gaming, or scientific computations, this reduction in CPU overhead can have a measurable impact on efficiency and responsiveness. The file system and package management strategies in small Linux distributions further contribute to performance advantages. Many small distros adopt minimalist file hierarchies and avoid bloated package managers that handle unnecessary dependencies or carry redundant libraries. For example, some distributions rely on package managers like Alpine Linux, which is designed for speed and efficiency, rather than heavier systems like apt or DNF, which handle a broader set of dependency resolution tasks and may require more storage space and CPU time. Lightweight package managers streamline software installation and updates, reducing I/O load and minimizing the risk of disk fragmentation or slow read-write operations. This approach also facilitates quicker system updates, allowing the user to maintain security and stability without suffering the performance penalties often associated with full-featured distros. Boot times provide another area where small distributions excel. Because small Linux distros initialize fewer services and employ simpler initialization systems, the time from powering on to reaching a functional desktop or terminal prompt is often dramatically reduced. Distributions designed with systemed or other lightweight init systems are optimized to parallelize startup processes efficiently while omitting non-essential services. Additionally, the use of minimal kernels tailored to the hardware ensures that the operating system loads only the drivers and modules necessary for the current configuration. This targeted approach contrasts with mainstream distributions that include extensive driver support, which, while comprehensive, increases boot times and memory usage. For systems where quick startup is critical, such as servers or embedded devices, these improvements in boot efficiency are significant and highly desirable. Hardware compatibility is another critical factor. Smaller Linux distributions often provide streamlined hardware support by including only essential drivers and kernel modules. While this may seem like a limitation, it actually improves performance on supported hardware because the system avoids loading unnecessary modules or handling unneeded hardware interrupts. For example, large distributions might automatically detect and initialize all possible network interfaces, graphical devices, and peripheral controllers, which can consume CPU cycles and add latency. In contrast, a small distribution optimized for specific hardware loads only what is necessary, ensuring smoother operation and lower power consumption. This is particularly beneficial for low-power devices, embedded systems, or older computers where system resources are constrained. Beyond raw performance, smaller Linux distributions encourage a philosophy of modularity and user control, which indirectly enhances efficiency. By default, these distributions install a minimal base system, giving users the freedom to choose exactly which applications, utilities, and services they need. This approach contrasts with mainstream distributions that pre-install a full suite of applications, ranging from office suites to media players, system monitoring tools, and developer environments. While convenient for new users, this abundance of pre-installed software contributes to bloat, consumes disk space, and introduces additional background processes. Small distributions empower users to build systems tailored precisely to their requirements, minimizing unnecessary overhead and maximizing performance for the tasks that matter most. The user experience in small Linux distributions is often smoother not only because of technical efficiency, but also because of psychological simplicity. By presenting a clean, uncluttered interface, these distros reduce cognitive load and avoid overwhelming the user with options and background noise. A lightweight environment means that menus load faster, windows open without delay, and system notifications are fewer and more purposeful. While this might not directly improve CPU or memory performance, it contributes to the perception of speed and responsiveness, which is an important aspect of overall system usability. Networking and internet-related performance are also positively impacted in small distributions. Large Linux distros often include numerous network-related services that run in the background, such as automatic updates, cloud synchronization, telemetry, and package index refreshers. While these services provide convenience, they generate network traffic and consume processing power. Smaller distributions typically omit these services or make them optional, allowing the user to maintain more efficient network utilization. This is particularly valuable in environments with limited bandwidth, metered connections, or older network hardware, where every byte of data and every millisecond of latency matters. Security considerations also intersect with performance in meaningful ways. By reducing the number of active services and minimizing the attack surface, small Linux distributions not only improve security but also reduce the computational overhead associated with monitoring, logging, and securing multiple services. Security features such as intrusion detection, firewall logging, and access control checks can consume resources when broadly applied. With a minimal system, administrators can focus on securing only the essential components, which streamlines both maintenance and performance. Additionally, because smaller distributions typically include fewer libraries and dependencies, the likelihood of conflicts, memory leaks, or inefficient code execution is lower, further enhancing system stability and performance. Storage efficiency is another tangible advantage of small Linux distributions. The minimal base installation often occupies only a fraction of the disk space required by larger distributions. This not only makes them ideal for systems with limited storage, but also improves file system performance. Disk operations are generally faster on less crowded file systems, as there is less fragmentation and fewer metadata overheads. Lightweight file systems commonly used in small distros, such as X4 with minimal journaling, BTRFs with selective features, or even Tiny Core's in-memory file system, contribute to faster read-write speeds and lower latency, which benefits applications ranging from office productivity to multimedia editing. Another aspect worth exploring is the influence of community and design philosophy. Small Linux distributions often target niche audiences who value efficiency, minimalism, and fine-grained control. Consequently, these distributions are crafted with careful attention to performance, avoiding unnecessary graphical flourishes, redundant libraries, or complex software stacks. Developers of small distros frequently perform rigorous benchmarking and profiling to ensure that every component contributes positively to system responsiveness. This contrasts with mainstream distributions that prioritize broad compatibility and feature completeness over raw performance. As a result, small distributions tend to be optimized not only at the architectural level, but also at the level of individual application integration, ensuring that system resources are allocated efficiently. Embedded systems and lightweight server environments offer real-world evidence of the performance advantages of small Linux distributions. Devices such as routers, IoT hardware, and single-board computers like Raspberry Pi often run specialized minimal Linux distributions precisely because mainstream distributions would be too resource-intensive. On these devices, every megabyte of RAM and every CPU cycle is critical. The ability of small Linux distros to provide full functionality while consuming minimal resources is a testament to their performance-oriented design. In server contexts, lightweight distributions allow administrators to maximize the number of virtual machines or containers that can run on a single host, enhancing scalability and efficiency. Small Linux distributions also excel in environments where responsiveness and uptime are critical. Desktop environments with fewer animations and simpler window managers respond more quickly to user input. Boot and shutdown sequences are faster, and system updates can be applied with minimal disruption. On servers, minimal systems reduce downtime caused by updates, reboots, or resource contention, leading to more reliable operation. Furthermore, when troubleshooting performance issues, the simplicity of small distributions makes it easier to identify bottlenecks, optimize configurations, and maintain predictable performance, unlike larger distributions where the complexity can obscure the source of inefficiency. From a software development perspective, small Linux distributions provide a cleaner platform for testing, deployment, and optimization. Developers can target minimal systems without worrying about hidden services, background processes, or unnecessary dependencies affecting performance. This is particularly valuable in performance-sensitive applications, including high-frequency trading platforms, real-time data processing, and gaming environments. By controlling the operating environment precisely, developers can ensure that software executes efficiently, making optimal use of CPU, memory, and storage resources. Another performance benefit arises from reduced graphical overhead. Large distributions with visually rich desktop environments often rely on GPU acceleration for effects like window shadows, transparency, and animations. While these effects enhance aesthetics, they consume additional GPU cycles and can introduce latency, especially on systems with older or integrated graphics. Small distributions, using lightweight window managers or minimal desktop environments, avoid these effects entirely, resulting in more predictable performance and faster rendering times. This is particularly noticeable when multitasking or running resource-intensive applications, where every millisecond of rendering counts. Energy efficiency is an often overlooked performance metric where small Linux distributions excel. By consuming fewer CPU cycles, less memory, and less GPU power, minimal systems naturally draw less energy. This translates to longer battery life on laptops and lower electricity costs for servers and workstations. In mobile and embedded applications, energy efficiency is critical, and small Linux distributions provide a sustainable way to maximize device uptime while maintaining acceptable performance levels. It is also worth mentioning the role of modularity in small Linux distributions. Many of these systems adopt a modular approach, allowing users to add only the components they need. This approach reduces resource contention and ensures that applications run in a clean environment with minimal interference. By contrast, larger distributions often include monolithic software stacks that introduce unnecessary dependencies, and potential conflicts, which can degrade performance over time. Modularity also facilitates better catching, faster load times, and more predictable behavior, all of which contribute to the perception and reality of higher performance. In practical terms, users who switch to small Linux distributions often notice immediate improvements in system responsiveness, application launch times, and multitasking capability. On older hardware where mainstream distributions struggle with sluggish performance, minimal distros can breathe new life into devices. On modern hardware, small distributions allow for highly optimized setups, where every system resource is available for user applications rather than background services or unnecessary graphical effects. This combination of technical efficiency, user control, and streamlined design philosophy explains why small Linux distributions are often preferred in performance-critical scenarios. In conclusion, the performance advantages of small Linux distributions arise from a combination of lean system architecture, efficient resource usage, minimal background services, lightweight desktop environments, targeted hardware support, modularity, and storage optimization. By avoiding unnecessary complexity, these distributions reduce CPU and memory overhead, improve boot and application launch times, and enhance overall system responsiveness. They empower users to build tailored systems that maximize efficiency, whether on older hardware, embedded devices, or performance-sensitive servers. Furthermore, the philosophy of minimalism and control encourages users to engage with the system intelligently, adding only what is necessary and avoiding bloat that can compromise performance. While mainstream distributions excel in providing a comprehensive out-of-the-box experience, the focus of small Linux distributions on efficiency, simplicity, and user control ensures that they often outperform larger distributions in terms of speed, responsiveness, and overall performance. The combination of technical optimization, practical design, and user empowerment makes small Linux distributions a compelling choice for those who prioritize performance and efficiency in their computing environments.